Hello and very warm welcome to this very short demonstrations of one of the most interesting Olympiads in chemistry, which has been taken in the year 2010 for the first round in the United Kingdom. I'm just going to look into this paper, which is for 2010. As you can see, I'm just scrolling down the page. I'm just going to, as a kind of a demo, just solve question number one. However, for question number one, as you're going to see, it comes with different parts. It has three different parts. Parts number one, which is going to be very straightforward. It's a basic general chemistry concepts that you have to know how to measure the molar of a compound, which is Ambrox, which is so easy to find it. However, for part B, which involves some technicalities of organic chemistry and the reaction mechanisms and the reaction pathways in order to predict compounds A, B, C, and D for compounds in these chemical pathways which they are orchestrated. I'm just going to focus for these demonstrations only on these parts to solve them. However, as I said, part A is extremely easy. Part B is a little bit tricky because you have to know that how to do the reaction pathways, how to work with different functional groups, and how to initiate organic reaction mechanisms, and how to just do some kind of changes along the way, depending if you are in acidic environment or basic environment, to let the reaction proceed. Then that's the purpose for this demonstration. Okay, now I just go back to the whiteboard that we have. I have copy-pasted the question structure with the small periodic table at the bottom, although we may not need to do that because this periodic table is heavily needed for the first part. Then you're looking at the molecular mass of each element. Now I'm just going to start right away to this question to find compound A. Now, as you can see in this question, for compound A, you have the molecular formula of the expected output. However, what do we need to do is that to show the pathways, to show the structure of the compound. Now, as you can see, our starting agent is dimethyl. You see that we have the O here, because of the presence of the hydroxyl group over there. The reacting agent is methyl sulfonyl chloride in a basic environment which is provided by pyridine, which is a Lewis base, which it means that it is willing to donate, I should say, the lone pair of the electron, or Bronsted-Lewis definition of the base, which it means that it's willing to accept the hydrogen ions, which is essentially a proton. Now, with respect to that, now we are just going to solve this one, and let's see how far we can just go for product A. Now, okay. When I have the dimethyl over here, and when we have also the reacting agents as methyl sulfonyl, I'm just going to put also the reacting agents here. We have the methyl sulfonyl here. I have the methyl group coming from here. I have lone pairs of the electrons for this double bond. Also, there is one double bond with the oxygen, and also we see that the presence of the chloride over here. Now, when we see that there's a chloride over there, because we have methyl sulfonyl chloride, I'm just going to start first with the agents that they have and see that how the reaction is going to proceed. But the most important thing that I have to look into when I'm just going to look into an organic reaction, the first thing that I have to look into is that to see if I can find a lone pairs of the electron, at least a lone pairs of the electron, which is not part of the hybrid resonance structures of the elements of the structure, which become confined in the structure, not easy to move, then as soon as I find a lone pairs of the electron, not confined in the resonance structures, and it's willing to move, then it has some motility there, then that's going to be the most important starting part of organic chemistry reaction analysis. Now, let's jump into these two structures to see that if I can find that specific lone pairs of the electron which has motility. When I look into this structure, the first thing which I can see is that it is the presence of the chloride. The presence of the chloride, which is, if you can see, the bound which I have here, this is somehow a very polar bound. Because if you can see on the periodic table, as you move from bottom to top, from left to right, the electronegativity increases, then you expect that the electronegativity of the chloride is significantly higher than the sulfur. Then as a result, you expect to have a partial negative charge on the chloride and also a partial positive charge on the sulfur. Transiently it happens. Now, when you are leading these reactions in a solvent to provide some energy for this reaction, then you see that this chloride, because they are part of, I should say, the 7 group of the periodic table, as we know that they are a good living group, then we expect that because of this huge contrast of the electronegativity, which leads to having this very highly polar bounds between them, the covalent bound dissociates. And when it dissociates, the electrons, which they are in these two parts, because I have one electron here, as I can say, because as you remember from elementary chemistry, these kind of lines that we have there in Lewis structures, each line represents one electron on one side, one electron on the other side. Now, if that's the case, when you dissociate a bound heterolytically, which it means that the bound is going to be just heterolytically dissociated, then these lone pairs of the these pairs of the electron, which is now part of this bound, it's going to all migrate to the chloride. Then what you expect to have is this: after these things happens, you may end up with this compound. First of all, I have my sulfur atom present there. I have these double bonds of the oxygen over there, and I'm just going to show these lone pairs of the electrons on these ones. And I have the methyl group there because it's methyl sulfur chloride, but however, when the chloride is dissociated, I have the chloride over there in a basic environment, which it means that we have this one, and it gets a negative charge. But something important has happened over there. And the important thing which happened over there is that I dissociated the bond. And I remember from basic chemistry that when you dissociate a bond, and when you form a bond, you have to stop and find effective charge on those two elements that they were impacted due to the bound formation or bound dissociation. I have two elements which are just impacted now over there. One of them is sulfur, and the other one is a chloride. Chloride is important. It's very easy to see that it gets a negative charge, but when I just go to this element, for sulfur, I'm just going to find the effective charge. I'm just going to do how to find the effective charge, if you have forgotten that. Look at that. It's going to be me. I'm standing on the head of the sulfur, which has lost the bound, covalent bound. I'm just going to draw a fishing net around it. That's how I just remembered myself for the formal charge and find the formal charge. In order to find the formal charge, I'm going to ask two questions from myself. The first question which I'm just going to ask from myself is that, what is the address of the elements which I'm standing on his head, which is the sulfur? What is the address of that? I mean, there is its address on the periodic table. If you go to the periodic table, you see the sulfur over here. It's below the oxygen. It means that group 6. Then I'm just going to write 6, which is the address of the sulfur, which I'm standing on top of it. The other question which I'm going to ask is that I see the net which I have drawn over here. I just count the number of the electrons which is inside the net. Each section which I'm going to cross, it's going to count 1 electron. You see that I have 1 electron here, 1 electron here, 1 electron there, and 2 over here. If you count them, you get to 5. Now I'm just going to subtract 5 from the address which I wrote over there. 6 minus 5, it becomes 1 plus 1. And that's going to be the effective charge of the sulfur, which I drawn over there. Now, I'm just going to erase this, and I'm just going to note to the fact that based on what I did over here, I just found the formal charge of the sulfur here as a positive charge. Now, you remember in organic chemistry, if you form a positive charge, invariably what do you mean? You mean that you have created structure which has a thirst and greed for electrons. That's why we call that what? Electrophile. It means that it loves the electron and it's electrophile. Now, on the other side, I'm just going to go back to this one. This is essentially what happened. As you can see, this is essentially what happens to my reactive agent, which is methyl sulfonate chloride. It turned to an ion, a positive ion, which we call that electrophile. Now, I just go back to this element which I had over there. If I just go to this element which I had over there, by the structure which I have over there, the presence of hydroxyl group here, it's very obvious. The hydroxyl group that forms alcohols. It's a very important functional groups. When I have the hydroxyl group, I remember from elementary chemistry that the oxygen comes with 2 lone pairs of the electrons on the oxygen. Now, these 2 lone pairs of the electron which I have over there, these lone pairs of the electron, they are forming, they give the structure a propensity and the property that it searches for the structures or the region of the structures that they suffer from electron deficiency. Now, if I just go back to this ion which I have formed, which is a methyl sulfonyl group which I have formed, you see that on the sulfur we have electron deficiency, and this is expressed by the positive charge there. Now, what happens is that one of these lone pairs of the electron is going to attack this sulfur here. It's going to attack this sulfur because, as I said, this is basic physics, and that's Coulomb law. The opposite charges are going to attract each other. They can just find itself in the vicinity of each other because if you remember, we said that we are in a solvent, a basic solvent, which is pyridine. Then, if that's the case, they can just freely find each other. The positive charge attracts a negative charge, and that's what we expected. This nucleophile, which it means that love the positive charge, is going to compensate for the electron deficiency of the methyl sulfonyl group over there. And this attraction all compares to what? It can be essentially translated into the fact that we said that, okay, it's going to form a covalent bond. We said that if this is the hydroxyl, I'm just going to show that here by this wedges over there. That's going to be the carbon here. Then I have the oxygen here. I'm just going to show hydrogen a little bit, I should say, away from that, because I'm gonna, for a purpose, you are gonna see why. I'm just gonna show the oxygen there. I'm just gonna show one lone pairs of the electron there. Okay, I do draw the lone pairs of the electron there. And you see that one of these lone pairs, now when the nucleophilic attack happens, it's just going to happen what? I'm just going to draw it with a different color in order to make it obvious. You see that there is going to be a bound. The nucleophilic attack, this lone pair is going to form a bound that it connects to the sulfur. Now, remember, I had 2 oxygen. And I don't forget that I have this bound over here, which can be the methyl group over here. Then there is a bound formed over there. Now, you see that when this happens, the result of this nucleophilic attack, which causes the formation of a covalent bound at the expense of the lone pairs of the electron, now they are formed a bound to form a bound here between the oxygen and the sulfur. I have formed a bound. And the question which I'm just going to ask myself is this. Now I formed a bound. There are 2 elements. They are impacted by this bound formation. And now that's the time to stop, take a deep breath, and lean back and find the effective charge on the oxygen and the sulfur. If that's going to be the case, I'm just going to again have my fishing net just go, for example, standing on top of the first element impacted by this bound formation. I draw my net around it, and I'm just going to go to ask myself 2 questions. The first question is this: what is the address of the elements which I'm standing on top of it? This is oxygen. In the periodic table, you see the oxygen is in the group 6. Then the address for that is going to be 6. Now, the second question which I'm going to ask myself is that how many electrons I have captured inside that fishing net. You see that I have 2 electrons over here. I have in this bound 3 crossing, which means there is 1, 2, 3. 3 plus 2 becomes 5. I have 6 minus 5 gives me plus 1. And that's effective charge on the oxygen there. Then now I'm just going to erase this. And I'm mindful that the formal charge, which I computed for, the oxygen is positive charge, which is a little bit weird. You're going to see that later because it's weird because when you have a positive charge on electron, which is the most electronegative elements, then you expect to have it reach with the electron. This positive charge shows electron deficiency. It's a little bit odd. Now we come back to that to talk about this. Now, the second element which is impacted by the formation of the bound in the midget color is a sulfur. I'm just going to go there, stand on top of it. Let me go a little bit over there. I just go stand on top of the sulfur. What I'm going to do is this. This is the bound which we formed. What I'm going to do is this. I draw my net around this to find the effective charge. The question which I ask myself is first, what is the address of the sulfur I'm standing on his head? From the periodic table, I know that it comes from group 6 because as you can see, this is right beneath the oxygen. How many electrons I have in my fishing net? I see there is 1 electron here, 2 electrons, 3, 4, 5, 6. Now I have 6 minus 6 gives me 0. Then it means that the sulfur, which suffered from electron deficiency as part of, methyl sulfonyl group, now it has become completely neutralized. And then as a result, it became highly stable when it becomes part of this bound. Now, what's going to happen next? The other thing which is going to happen next is this, that now I go back to these structures which I had. Let me clear a little bit this structure to give it form a little bit bare, have a bare structure. It has double bounds. Now, I go back to this one. I see that there is a tremendous wrong thing happen. The presence of the positive charge on the oxygen, and as I said before, because oxygen is a highly electronegative element, when you look at the presence of positive charge on it, which signifies the electron deficiency, you should be a little bit surprised. For example, you're going to see someone very rich that you know from your families, someone who is a millionaire, now he's begging for the money. And that's the same story for the oxygen with the positive charge. Oxygen, which is rich with electron, now is deficient of the electron. Now we have to resolve it. And that's where the trick comes from. That's where we should not stop. That's where we should not stop. The thing that is just going to happen is this. We have two options to do. Either we are just going to sacrifice a bound. We have three bounds to sacrifice. There is one bound between the oxygen and sulfur. If you are just going to sacrifice the bound because oxygen is more electronegative than the sulfur, then if you heterolytically cleave the bound and you say that the oxygen, for example, grabs the electron from the sulfur, if that's going to be a hypothesis, because it's going to be a very energy-consuming reaction and you have not provided external heat, then you see that this path is not feasible. The same story with this. You say that I'm just going to cleave the bound between the carbon and the oxygen, and the lone pairs migrate towards the oxygen, because oxygen is more electronegative, then again it's not going to be possible, because cleaving the bound between carbon and oxygen in the room temperature as we are in that question in the Olympiad is not possible. You need extra heat as a source of the energy into the reaction to induce the breakage of the bound. We do not have it provided, then this one is not possible. Then the third option, which is possible for us, probably is the bound between the hydrogen and oxygen, because hydrogen is the least electronegative element, and oxygen has high electronegativity. This huge contrast, this stark contrast of the electronegativity between the hydrogen and oxygen, it induces almost the cleavage of the bond, provided that you are in the solution, which is basic. Look at that. We have two motivations for that. The presence of the pyridine as a solvent induces, and there are two things. I have to come back again to that. The presence of the basic solution, which is pyridine. Look at that. This is the basic solution, both from the perspective of the Lewis basicity and Bronsted-Lowry basicity. And the contrast of the huge contrast of electronegativity between hydrogen and oxygen, you see that this bound very easily cleaves heterolytically, and the electron is going to be deposited back into this one. And the hydrogen is going to be taken up by this basic environment which we have there. Then as a result, for the first part of this reaction, what we end up is this. Let me use a different color, as I'm just going to write the final for bounds that we are just going to form. The methyl group is going to be there. This stoichiometric, I should say, this stoichiometry is going to be there. This methyl group is going to be there. This one, it goes to the oxygen now, which now it has two lone pairs, because one lone pair came from this bound, and now also you see that. Let me just go with another color, show the methyl sulfonyl group. We have sulfate, we have double bound with the oxygen, and we have the methyl group part of this one. And that becomes essentially the final products, which is going to be for products A of that reaction, which was essentially question 1 of year 2010 of the Chemistry Olympiad in the United Kingdom. Then you see that if we just go there, you see the structure has been shown in terms of the molecular formula, but compound A doesn't represent the structures. And in order to infer the structures, the inference, in order to make it, you need to know substantial knowledge about basicity, acidity, nucleophilicity, electrophilicity, the concepts of the leaving group, and the more important thing is that how to induce and start the organic reactivity by finding a suitable lone pairs of the electron, which is not part of a hybrid resonance structure.